So for this video, I'm going to go through some of the review questions and work them so that you can follow along and try to understand how these things are put together through direct example. So for the first question, we have some x and y data that are given to us, and we're going to interpolate it to some other values that we don't have in the original data. And then we're going to plot the interpolated data as lines and the given data as symbols, and try to make the plot look good by labeling the plot axes. So this is interpolation. We're going to need to load the libraries for interpolation from scipy.interpolate, import interp1d. Now, the interp1d function takes our data and returns a function for interpolating. So I'm going to call it fi equals interp1d, give it the x data, the y data, and then we want to evaluate the function at the interpolated data point. So yi be equal to fi evaluated at xi. We need to run the cell. There we go. And then we can plot the results. So we do, I guess let's import the plotting functionality, %mat plot lib inline. And import matplotlib.pyplot as plt. We can do plt.plot x comma y with data points, and plt.plot xi comma yi as lines, plt.x label, plt.y label y, excuse me. Let's see what we got. Okay. And we can put a legend on there, plt.legend, data, interpolated points, and we'll put location equals best. And that'll go ahead and plot it up. And so there we go. That's all there is to it. This does a linear interpolation. If we wanted to do a spline, we'd come up here to the interp1d command and write kind equals cubic. And then you can see instead of straight lines between, you kind of get these cubic, more smooth curve. Okay, problem number 2. For that data that was in problem 1, let's fit a second order polynomial to the data, and then we'll evaluate the polynomial points xi and plot it as before. So we can do, in this one, the functions are polyfit and polyval, and those are available in NumPy. So we'll do, we want a second order, so we'll call it P2 equals polyfit x comma y comma 2, and then yi equals polyval P2 comma xi. Oops, you can see I didn't put np dot, and then it worked. So now let's go ahead and plot it up. Dot plot x comma y, plt dot plot xi yi lines, plt dot legend data polyfit, location is best, x label x plt.y label y. And there you go, single second order polynomial through the data. Write a print statement that outputs the polynomial. So for that, if we go print p2, you can see that it's got the coefficients. But let's go ahead and make that a little bit pretty. So the polynomial fitted equals a number, x up squared, plus another number, x plus another number, and then give it the numbers. P2, 0, P2, 1, P2, 2. And there's a formatted print statement for the polynomial. Okay, so now we want to do this in Excel. Let's go ahead and grab the data so that we can use it. Print x, print y. Okay. Actually, let's go print np.vstack x comma y dot transpose. That'll be a little easier for Excel. Just copy that. And then we'll go into Excel, paste it in. And we can go to data, text to columns, delimited, next, space, finish, and get rid of the junk. We don't need that. Or those. And it looks like some of these didn't work, so let's just fix that. Those didn't have spaces, so my delimiting didn't help. We don't need that or that. And these can just move these over. Great, so now we have our x and y data. Now for these, we can plot these up. Charts, pick the scatter plot. We'll go right click, add trend line, polynomial, second order, options, display the equation on the chart. Okay. If you kill the lines, increase the size a little bit. Maybe. Zoom in. No, that didn't work. We can always just bump it up this way. There. And there's our polynomial. And just for fun, we can compare 2.4969, 2.4969, 14, and 30. Sure enough, about the same, basically the same fit. For problem 4 here, we want to fit a second order polynomial to the data using the more general curve fit function. So to do that, we need to first define the function we're going to fit. That function will be basically this one, but those will be a, b, and c. That is, we have f of x equals ax squared plus bx plus c. Ax squared plus bx plus c. So to do this, we define the function def f of x. Now for general curve fitting, we then add the parameters as extra arguments, a, b, and c. And then we just go return a times x squared plus b times x plus c. And then we can go the parameters and some extras equals curve fit the function. And let's see, I need to include a library here from scipy.optimize import curve fit. Okay. And it takes 3 arguments. I only gave it 1 argument. So because I don't remember, we'll type curve fit question mark. Oh yeah, duh. It wants the x and y data, of course. So we got to tell it both the function and the data that we're fitting it to. So that's x and y. And there we go. And then if we want to plot the data, we can do the same thing as before. Let's go steal that plot. plt.plot, copy. But here we'll do yi equals f of x and params 0, params 1, params 2. So we'll evaluate the function using our now optimized parameters. And then when we plot this up, let's see, just take xi also. X and y must have the same first dimension. Oops, that's the problem. I did x instead of xi. Okay. And there we go. And we can look at them, params, and sure enough, we get basically the same parameters using genfit as we had for the polynomial. 2.4969, 1497, 30.2. So there's genfit. And then finally, we can solve the same thing in Excel using the solver. So let's go back to Excel, define some parameters, A, B, and C, give them some initial guesses, 1, minus 5, and 30. And then we'll, maybe over here, we'll go y fit and write in the function equals A, $sign that, times x squared plus b, $sign that, times x plus c, $sign that. So there's our curve fit, double click, it looks like we did that right. We can find the square error between the actual data and our data, so equals the real data minus our data, square it, double click the box to fill down, find the sum of the square error equals sum of this column, and parenthesis. Now we'll go up to the solver, tools, solver, and we'll say, okay, set this thing to be minimum by changing these cells and hit solve. Says it found a solution, but I don't really like it. Let's see what happens if we put 2.4969 minus 15 and 30. 2.49. And let's go ahead and plot up our fit also. There's y, there's our fit. Tools, solver. we must not have had a good enough initial guess. So take the objective, make it minimum by changing those cells. And it's still not really doing it. So here the square error is 21280. Oh, hang on. Maybe the problem is make them non-negative. That's the problem. So it was trying to minimize it where none of the parameters could be negative. And that doesn't make sense for this problem. That was a default from a previous case. So this time it works just fine and recovers the same variables we had before. If we do what we had, which was minus like 5 and 10 or something, and resolver it, it'll zone in on the correct values again. You did a pretty fine job. Okay, you have to be a little bit careful with how you interpret the sum of the square error, because this may or may not be close to 0. Its actual value is somewhat arbitrary and depends on what the value of the y variable that we're dealing with is. And so just because this thing doesn't look like it's close to 0, it doesn't matter. It's close to 0 in a relative sense. Or it's as small as it can be for fitting this particular function. So that is it. That's the review using both some of these questions in Python and in Excel.